Welcome! We're starting a new lesson of statistics. We're almost at the lesson 10 and we're currently in lesson 9, almost ready for a big celebration, a big small celebration. Today we are going to discuss the box plot, also known as the box and whiskers plot. In the last lesson we talked about measures of relative position, if you remember, and we briefly touched on the topic of the box plot. Today we'll talk in more detail about this graph and all of its details. For this lesson, be prepared for many examples and hopefully fun visualizations of this type of graph. In this video, we will try to answer questions that you may have about the box plot, such what is a quartile and how to interpret it, how to interpret a box plot, what is the box plot for, how do we identify outliers in a box plot. If you're curious to discover more about these topics, stick around and watch the video with us. Today's agenda has 4 topics, starting at the quartiles, going to box plot theory. We will then see how to interpret the box plot, and in the end, let us interpret some examples of box plots together. So let us begin by the section quartile calculation. Imagine we want to calculate the quartiles of a dataset. We can be interested in all kinds of data, as long as the data is numerical, something that we can count or that we can measure over and over again, repeated times. Here are some examples of data you might want to collect and study. For example, the volume of sales of music CDs of a given musical artist, such as for instance Shakira, over the last year, or the electrical consumption per household in a given region, or the number of votes for the last election in a given country. The amount of water drunk per day by the population of a country. In this different context, the concept of quartile is applicable and it's very useful. But you remember what is a quartile, how many quartiles there are, and perhaps the most important question, how do we calculate a quartile? We often come across with different methods of calculating quartiles. These different formulas often lead to different results in terms of quartiles, and consequently different quartile values for the same set of data. If we try to use automatic algorithms to determine the value of the quartiles, for example, Excel, SPSS, or Python libraries, we may even get different answers. A brief example in Python. I'm going to use 2 functions from 2 different libraries, statistics and NumPy. I have my data vector with 9 elements. In one case I use the quantiles function, in the other I use the quantile function. When I invoke or call these functions, the results are different. Have I made a mistake somewhere along the process? No, that's just how it goes. As we will see, this is because my number of elements is odd, 9 elements, and therefore this poses more problems than if the number of elements was even. Consulting the literature on these 2 functions, we can see that one uses the exclusive calculation method and the other the inclusive method. This difference of methods in general, whether in college, faculty, or even technology, often leads to confusion and can generate a certain mistrust in statistics. You'll often find mathematics and programming forums discussing this issue. What happens is that there is no universal agreement on the selection of quartile values, on how to divide the ordered dataset into 2 halves and then halving it. If there are a number that is even of data points, all the methods will give the same result. But if there is an odd number, Then we'll see our mathematical friends discussing formalisms and philosophy without reaching an agreement for several hours. So, what are quartiles and how are they calculated? At least according to two of the most famous methods, exclusive method and inclusive method. In a simple, but still not very rigorous way, we can define quartiles as the values that divide the dataset into 4 equal parts. The problem is that in a small dataset, for example, a dataset that has the values 1, 2, 3, 4, 5, both 1.5 and 1.6 are valid candidates for quartile 1. As the data is sparse, 1.6 also divides the data into 2 subsets, one with element 1 and the other with element 2. Of course, the value 1.5 is more in the middle and a more sensible value, but according to our broad definition, 1.6 could also be a valid choice. But let's talk in general terms. When calculating the quartiles, we always need to sort the dataset. This step should not be forgotten because it is essential for us to have correct values. So imagine 1 million people telling you how much they earn. That's millions of numbers that we need to sort out before looking at the quartiles. Once the data has been sorted, we look for the second quartile. By definition, the second quartile is the value that lies in the middle of the elements of the dataset, the value that divides the dataset into 2 equal parts, halves. In the case of our salaries, it is the salary that divides the sample into 2 equal parts, one with 500,000 people earning a lower salary, and the other with 500,000 more fortunate, let's call it like that, workers. Note that the median salary is not the average salary. The calculation formula and the concept of average and median are very different. In this context, the first quartile will be the value in the middle of the first half of the dataset, and the third quartile will be the value in the middle of the second half of the dataset. So far, so good. In the examples of salaries, the first quartile will have 25% of the data below it, that is, 250,000 people, and the third quartile will have 75% of the data below it, that is, 750,000 people. Above it will be the highest paid 250,000 people. But let's look at this with an example that will be a little bit more abstract, but probably more enlightening. Let's consider the following data, already sorted in ascending order. We have a total of 10 elements, so the middle of the values will be between the 5th and the 6th element, that is, between 12 and 16. The midpoint between 12 and 16 is 14. This value, the 14, divides the dataset into 2 halves and represents the second quartile. As a note, the second quartile or the median is always calculated in the same way with any possible method. The calculation formula is universal and very well established. Remember that quartile 2 is always the same value for a given set of data. Quartiles 1 and 3 can be calculated differently. Now, back to our example. The first quartile will be the value in the middle of the first subset. This subset has an odd number of elements, so the value in the middle is an element of the subset. The element in the third position is 5, so the first quartile is equal to 5. In the same way, the third quartile will be the value in the middle of the second subset. Once again, as the number of elements in this subset is odd, the value in the middle is 23. So far, we've had no problems. But what if the dataset has an odd number of elements? That is where the problems begin. Remember, with an even number of elements, we always have an agreement, but with an odd number of elements, we can only agree on the median. Note that the set of data that I bring to you is similar to the previous ones, but without the last element. As the number of elements is odd, the second quartile will be the central element, that is, the value in the fifth position, which is 12. So far, so good. But now, how do we divide the dataset into two halves? The fifth element must be included in both halves, in neither half, or on just one of them. We don't know. This uncertainty gives rise to two different methods of calculating quartiles. These are the most famous and widely used methods, the inclusive method and the exclusive method. In the inclusive method, the element corresponding to the second quartile is included in both halves of the dataset to calculate the quartiles, quartile 1 and quartile 3. As we have included the median value, we transform the sets into sets with an odd number of elements. The median value for quartiles 1 and 3 will be exactly in the middle of these subsets and will come out very easily from the data. In turn, in the exclusive method, when the data has an odd number of elements, the element corresponding to the second quartile is not included to calculate the quartiles. This leaves us with two subsets with an even number of elements, which can complicate the formula for calculating the quartile. We can average the two middle points, which is the procedure chosen by the exclusive method. We'll go on to talk about other ways of calculating quartiles very shortly, but before we do that, let me take a moment to talk about the concept of position of quartile and the value of quartile. A quartile has a position or location in the dataset. In the example of the 9 elements, we have 9 integer positions from 1 to 9. Between position 1 and 2, we have other positions, such as, for instance, 1.5, 1.6, and so on. We can always locate our quartile in any non-integer position. It doesn't have to be an integer position corresponding to an existing value in the data. That's not mandatory. The quartile also has a value, the concept of value, which represents the element in question. The process of calculating each quartile includes two steps. First, we determine the position of the quartile in the dataset. Second, we calculate the value of the quartile. Each of these problems can be dealt differently, giving rise to a multitude of different methods. Importantly, when the quartile coincides with an element of the dataset, we say that its position is an integer value. In that case, the quartile value is immediate. For example, for the initial dataset with 10 elements, the position of the second quartile is at position 3, so it's the value of 5. When the quartile is between two elements, we say that its position is a non-integer value. Also in the dataset with 10 elements, the position of the second quartile is between the elements in positions 5 and 6. So its position is 5.5. In this case, it is necessary to calculate its value by averaging the values of the elements in positions 5 and 6. The position of the quartiles can be calculated mathematically and in formal terms. All methods, whatever they are, determine the position of the median, the second quartile, in the exact same way, as we have already said. Therefore, the position or the location of the second quartile in a dataset with n elements is n plus 1 over 2, This can result in an integer value or a non-integer value position. The manner to determine the position of quartile 1 and quartile 3 in a dataset depends according to the methods that we use. Here are the formulas for calculating the positions of the first and third quartiles corresponding to the inclusive and the exclusive methods. Here we have the calculation formula for each quartile depending on whether we have an even or odd dataset. Note that where the methods differ is when working with data with an odd or even number of elements. This is a table for calculating positions. The formula for calculating the value of a given position can also vary. For the inclusive and exclusive method, once the position is known, the way to calculate the quartile value is the same in both methods. The table below shows how we calculate the quartile given its position, integer or non-integer, in the dataset. In short terms, if the position is integer, it's easy to get the element because it exists in the data. If the position is not an integer, we have to average the two closest neighbor values. There are many methods for calculating quartiles besides the method exclusive and the method inclusive. And they differ, or they can differ, in both the first step of the process, when we calculate the position of the quartiles, as well as in the second step of the process when we're calculating the value of the quartiles. When the quartile position in the data is not an integer, the inclusive and exclusive methods calculate the average of the values of the elements in the data closest to the quartile position. However, there are methods that round the position of the quartile so that it's always equal to one element of the dataset. And there are different methods for performing a rounding of a number. Other methods choose to interpolate the values of the elements closest to the quartile position. For example, if the quartile position is 2.85, interpolating the quartile value would give 0.85 multiplied by the second element plus 0.50 multiplied by the third element. With this, we conclude our section on calculating and defining quartiles, and we will go now for the second section. Recalling the box plot. If you've seen the previous lesson, you probably have a pretty good idea of what is a box plot. If you haven't seen the lesson, you've missed a fantastic lesson, an amazing lesson, but you've probably heard of the box plot and probably found the name of the graph even curious, right? In statistics, the box plot is a graphical way of representing the distribution of the data for a single variable using several types of information, including the quartiles. It should be noted that we are dealing with a single value whenever we use a box plot. One dimension. For example, if I survey the gender, the age, the weight, and the height of my YouTube viewers, each of these variables could represent a different set of data. So far, we're not going to correlate different variables, but we're going to study them in isolation. And I will give a little brief introduction to the history of Boxplot. It was initially developed by John Tukey, and the Boxplot is also known as the extremes in quartiles diagram or the box and whiskers diagram. This chart serves the same purpose as an histogram, although unfortunately it doesn't allow us to see the total shape of the distribution. Because essentially we are limited to the concept of the box, and that doesn't show all the different oscillations of the distribution. We will now explain how to interpret a Boxplot, what conclusions we can draw when we analyze a chart of this type, and how the box plot shows outliers, among other subtopics. The box plot provides a lot of information, and perhaps this explains why it's not trivial to understand and to interpret a box plot. In practical terms, we have information about the following characteristics of the dataset: central tendency, dispersion, asymmetry, tail length, and outliers. This is a lot of information, and how do we collapse all of this? A box plot shows 5 statistics: the minimum, the first quartile, the median, the third quartile, and the maximum. These values are called in statistics as the 5-number summary. As we will see, the box plot also shows the outliers. If we show the outliers, the minimum and the maximum are replaced by extreme values calculating using a specific formula. But let us first see how to create such a chart. To construct a chart of this type, you draw a rectangle aligned vertically or horizontally with 2 straight lines, which we call the whiskers, one on each of the opposite sides of the rectangle. The height of the rectangle is defined by quartile 1 and by quartile 3. A line bisects this rectangle at the median value, that is the second quartile. The semi-straight lines connect quartiles 1 and 3 respectively to the minimum and maximum values of the dataset or to the extreme values. So now let us go to section 3, where we will see how to interpret the box plot. With only 5 numbers, 3 of which have we already seen how to calculate using the quartiles, and the other 2 resulting from a simple observation of the data, the maximum and the minimum value, we can get a very enlightening representation of how the data is distributed. The box plot is also very useful for comparing different sets of data, as for example when I want to compare the salaries of men and women in a given company. So let us take a closer look at the possible interpretations we can make out of the data with the box plot. Regarding measures of central tendency, the center of the distribution is indicated by the median line in the center of the square of the box. Sometimes we also have information about the mean, but this piece of information is optional and we don't necessarily always have it in the box plot. The dispersion in turn is represented by the amplitude of the graph, calculated as the maximum value minus the minimum value. We can also see from the size of the box what the dispersion of the most concentrated data around the center is, 50% of the data to be exact. The position of the median line in the rectangle tells you how skewed the distribution is. A symmetrical distribution will have the median in the center of the rectangle. If the median is very close to the first quartile, then the data is left skewed and asymmetrical. If the median is closer to the third quartile, the data is right skewed and asymmetrical. Message: if a sub-box, whether above or below the median, is relatively small, this means that the data is very concentrated in that area. Otherwise, the data is more dispersed. These notions are not obvious and are somewhat complex, but with experience and training, we can learn to analyze the symmetry of a box plot very precisely. Let's talk about how to interpret outliers or discrete points at typical points. Outliers in a box plot appear as dots or asterisks, stars, or any other symbol outside the lines drawn. Outliers are any values that are far beyond the highest concentration of data. Once again, there are many ways to identify whether a given point is an outlier. A simple formula consists of applying the following formulas to a case study. The outliers will be the values outside the quarter 1 minus 1.5, the difference between quarter 1 and quarter 3, and quarter 3 plus 1.5 multiplied by the difference between quarter 3 and quarter 1. If you notice, we are defining a range which by definition will always be greater than the amplitude of the box, the central box, the difference between quartile 1 and quartile 3. The range we have defined will cover a large percentage of points, but will eventually leave some out, the atypical or discrepant points. In this case, the limits of the whiskers will not coincide with the maximum and minimum values of the set. They are just the largest and smallest values in the set that have not been classified as outliers. As the whiskers must forcedly end at an observed data point, the length of the whiskers may appear unequal, although the size of the whiskers is the same for both sides. The calculation is the same. So let us now take some time to interpret Boxplot together. And I will give 3 examples, the first one being about global warming. As you know, it is a big problem and several researchers have tried to study the temperature of the Earth's atmosphere in order to demonstrate climate change. And one big problem related to climate change is CO2 emitting vehicles. In a study, they compared 3 fuels, the gasoline, diesel and an alternative fuel, to understand which fuel released the most CO2. In other words, which one contributed the most to global warming. And in the chart we can see that in terms of central tendency, gasoline and diesel emits the greatest amount of CO2. This is because the median emissions are relatively similar. This information can be used to help combat or fight global warming in different ways, such as by changing the formulas of diesel and gasoline. With the box plot, you can visualize and compare several sets of data. Obviously, in order to compare 2 variables, they have to be related somehow. But assuming that is the case, it's much simpler to use a box plot than to compare several histograms directly. For example, we also have an example of the salaries of workers grouped by gender. The 2 box plots are different, but they are related, as they deal with the topic of the wage or salary. You can see that the ranges of salaries for women is greater than for men. Interestingly, the maximum amount earned is higher for the study group composed of women. Unfortunately or not, this is also the case when we look at the lowest salary. In general, the central tendency of men's salary is also higher than human salaries, and all of this information you can get from comparing the 2 box plots. Finally, and going through the last example, we analyze a classical example in statistics which has to do with every time we need to evaluate a group of students. In the box plot that I show here, we can immediately see the following information. By looking at the chart, we know that 25% of the scores are less than or equal to 63 points. So 25% of the students scored less than 63 points. And by looking at the box plot in general, we can see that the test was relatively easy, because, for example, 25% of the scores are greater than 85 points, and in general, 50% of the grades are between 63 and 85 points. There is some bias in the chart because, for example, to the left we have the data more dispersed and to the right we have the data more concentrated. Note also that the whiskers have different sizes because we are ignoring the method of the outliers and we are calculating the minimum and maximum values of the set to define the whiskers. Here we show three box plots corresponding to different types of data. And if I asked you which distribution, which example has the distribution that is more well behaved, more symmetrical, what would you say? The symmetrical distribution is in fact the first. This is because we have 25% of the data to the left and to the right, approximately at the same distance. In the second example, we have an asymmetrical distribution. And why? Because we have 25% of the data much more concentrated on the left than on the right. This is called left skewness. The third example is one of right skewness. We have an extreme bias to the right in this case. And as we end this lesson, I'll leave you with a phrase that has been attributed to the creator of the Boxplot, John Takei. Eventually the phrase wasn't even said by the author, but it's still interesting and comes well with the content of the lesson. Overall, we hope that you had fun, learned a lot about the Boxplot and about statistics. Thanks again for being with us. See you in the next video.